Hello students. So today we are going to study one more important law of magnetostatics, and that is Faraday's law of electromagnetic induction. Right? So before going to the Faraday's law, let me know what do you mean by electromagnetic induction. Right. So this concept we studied in our previous classes for a bite. That is, you know the basic concept that whenever in a current carrying coil, current is flowing, there will be the production of magnetic field around it. Right. So when this magnetic field is created, you know that we represented it with respect to some lines. Right. So we considered a magnet and we showed the lines like this, right? So these magnetic lines will represent what? Magnetic field or the strength of magnetic field. So this, when these magnetic lines of force are cut by any closed circuit, so at that time one current is induced in this circuit. That means what? Whenever this magnetic flux or this magnetic lines is nothing but how many numbers of lines are there, that only is magnetic flux. So when this magnetic flux is changing, right, with respect to that, in the coil a current is induced or the EMF is induced. So the EMF which produces this current is called as induced EMF, and that phenomena is called as electromagnetic induction. Right? Changing magnetic flux will produce an a current in the circuit, an EMF in the circuit. That only we are studying here in detail. So before going to anything, what Faraday did, what Faraday observed in his experiments, that we have to analyze first, right? So what I'll do, let consider one coil, one current carrying coil. First considered one current carrying coil, okay, and this coil is connected to a galvanometer. Coil is connected to a galvanometer. Okay, so here in this coil like this current is flowing. Okay, so now what I will do, one magnet, let's consider one magnet. Okay, one magnet is there and its north pole is facing the coil. So when this magnet is moved towards the coil, when this magnet is moved towards the coil with its north pole facing the coil, the galvanometer shows the deflection in this direction. Okay, so when the same thing happens like this, again north pole and again the coil and the galvanometer. So now here what happened? The magnet is moved towards the coil. Now when the magnet is moved away from the coil, when the magnet is moved away from the coil, the galvanometer shows the deflection in opposite direction. Understood? So now if the experiment is repeated with the south pole, means in the place of north, if you put south, if you put south here, the deflection will be in this direction when it is towards the coil. So if you put south here and when it is moved away from the coil, the deflection will be in this direction, means the directions of the galvanometer's deflection are reversed, right? So if the magnet is stationary, if the magnet is at rest, it is not moving neither towards the coil nor away from the coil, so at that time deflection in the galvanometer is also constant, or there is no any deflection in the galvanometer. Again we can observe that these deflections increases with the velocity of this magnet to the coil. Means if it is moving fastly away from the coil, the deflection will again increase. If it is fastly moving, velocity increased, again the deflections are increasing, right? So These are the observations. What are the observations? The very first observation is what? In Faraday did this experiment by considering one magnet and one current carrying coil. Okay, so when the magnet is moved towards the coil, galvanometer shows the deflection in one direction. The same way, when the magnet is moved away from the coil, the galvanometer shows deflection in the opposite direction. This is our first observation, right? The second observation, when we repeat the experiment with the south pole of the magnet is facing the coil, then the deflections in the galvanometer are reversed. Second observation. Third observation, when the magnet is stationary, there is no deflection in the galvanometer. Fourth, when the magnet is when the magnet is moved fastly, means when the velocity of the magnet related to the coil is increasing, the deflections will also increase. And the last point we can observe here, that the same things happen when we kept the magnet stationary and when we move the coil. Fifth observation is what? Keep the magnet stationary and move the coil. Now, if the magnet north pole is here and you are moving the coil towards the north pole, then the deflection is in this direction. North pole is here. When we are moving the coil away from the north pole, deflection is in this direction. Same happens for south pole in the reverse directions. This is the fifth observation. So this is the first experiment done by Faraday. First experiment done by Faraday. Another experiment he did. Another experiment. So, in his second experiment, what Faraday did is he considered one primary coil. Okay, let me draw a primary coil first. Primary coil P. And this primary coil P is connected to a battery. Again, further it is connected to a tap key. Tap key. Okay. So now in this primary coil, current is moving. Okay. Again, a secondary coil he considered. What? A secondary coil. And this secondary coil is connected to a galvanometer. Okay, this is P and this is, yes, primary coil and secondary coil. Okay, so now in this experiment, what Faraday observed? Okay, so now here it is the battery and it is the tap key. So this tap key, why it is used, you know it. It is used to make and break the circuit. Means if this is tapped, the circuit is made. If this is not tapped, the circuit is broken. So when this tap key is tapped, means you may use the tap key in any experiments. No, you can understand. So when it is tapped, at that time what happens? Means by pressing the key K, the galvanometer shows the deflection in one direction, in any one direction. When this is pressed, means it is like this. When it is pressed. So in the same way, okay, let me draw it once again. Again here we are having primary coil and here we are having tap key and here we are having secondary coil and that is connected to galvanometer. So now here what we have done, we have pressed the key and the galvanometer showing the deflection in this direction. Now what happened, this is not pressed, key is open. So at that time galvanometer shows deflection in this direction. Means when the tap key is pressed, the galvanometer shows direction like this. When the it is not pressed, it is open, the galvanometer shows the deflection in opposite direction. So what we can understand by this observation is, if the current in this primary coil flows continuously and there is no any deflections produced in the galvanometer. Understood? Means when you are not making or not breaking the circuit, there is a constant current flow in the circuit, then the galvanometer shows no any deflection, constant current is flowing. But when the key is pressed, galvanometer shows deflection in one direction. When the key is not pressed, the galvanometer shows the deflection in opposite direction. So when you are not doing anything with the tap key, if there is no any tap key only and the current is flowing uh, continuously constant current is flowing in this circuit, then this galvanometer shows zero deflection, no any deflection. So the deflection is observed only when we are making and breaking the circuit. Understood? So the same things are observed while increasing or decreasing the primary current or the relative positions of the coil. So this you see here, this primary coil and secondary coil, they are not connected to each other, right? They are not exactly connected to each other, but to this whole circuit is assumed to be the single one. So what we can observe by these two experiments, whatever I explained, what we can observe is, listen carefully, what we can observe is, whenever a magnetic flux through a conductor, whenever a magnetic flux through a conductor is changed, an EMF is induced in the conductor, right? And the magnitude of the induced EMF is equal to the rate of change of magnetic flux through the circuit. See here, this coil, you are moving away or moving near, you are moving near or away, that means what, this magnetic flux is changing. No, what is magnetic flux? Number of magnetic lines. What are magnetic lines? Magnetic field. So if this is moved near to the coil, there is magnetic field. So if there is magnetic field, there are magnetic lines of force also. So if there are magnetic lines of force, means that only is nothing but magnetic flux, na? So when it is near to the coil, the flux is more. When it is away from the coil, flux is less. That means what, this magnetic flux related to this coil is continuously changing, right? So if it is changing, the galvanometer is showing the deflections. So that deflection is nothing but what, electromotive force of the current. So the change in magnetic flux will induce an EMF in the circuit, and that EMF's magnitude means how much EMF is produced, means how much change is observed here. Whatever the change is observed here, that only is produced as the EMF. So the magnitude of this induced EMF is equal to what, rate of change of the magnetic flux. So what we can write here, if pi is the magnetic flux through the circuit, right? If pi is the magnetic flux through the circuit, then that is directly proportional to, sorry, if pi is the magnetic flux in the circuit in the time t, and epsilon is the induced EMF. Epsilon is the induced EMF and pi is the magnetic flux in the time t. So what I said, this magnitude of EMF is nothing but rate of change of magnetic flux. Magnitude of how much EMF is produced means how much magnetic flux is changed. So the induced EMF is directly proportional to rate of change of magnetic flux. So by this experiment we can write here that the induced EMF is directly proportional to rate of change of magnetic flux. Understood? This is the first observation by the Faraday's experiments. Okay, and the second observation is what? The direction of this induced EMF is opposite to the change produced. Means, see here, if the magnetic flux is, if the EMF is produced in this circuit, the EMF's direction will be opposite to the change in magnetic flux. Here also, the EMF, the produced EMF, the induced EMF, its direction is also opposite to the magnetic flux produced over here. Right? So this we can write here as epsilon is equal to minus d pi by dt, because the induced EMF's direction is opposite to the change in magnetic flux. So here in the second observation we are writing the direction of the induced EMF, right? So here only in these two observation only I got two laws. So let me know you first, what is this? Whenever the magnetic flux through a conductor is changed, an EMF is induced in the conductor, and the magnitude of the induced EMF is equal to the rate of change of magnetic flux through the circuit. This only is called as Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. And here we give the direction. No? Means the direction of the induced EMF is such as to oppose the change that produced it. Means this only produced this. So its direction is opposite to the change produced. Understood? So this direction of the of the induced EMF is also called as Lenz's law. Understood? So once again I will tell you, Faraday's law means whenever the magnetic flux through a conductor is changed, an EMF is produced in the conductor, and the magnitude of the induced EMF is equal to the rate of change of magnetic flux through the circuit. This is Faraday's law. Second is the direction of this induced EMF or induced current is such as to oppose the change that produced it. So epsilon is equal to minus d pi by dt, and this law which gives us the direction of EMF is called as Lenz's law. Understood? So this is the some two important laws: Faraday's law of electromagnetic induction and Lenz's law. Okay, so here in the second experiment we observed that these two coils are related to each other in any manner, right? So what is the theory in that experiment, that we will study in the next class. That will there comes the concepts of self inductance and mutual inductance, that we'll study in the next class. Okay, so at the last, so I already told you that this chapter is divided in 4 parts: magnetostatics, magnetic properties of the materials, electromagnetic induction, and alternating current. So magnetostatics is complete, magnetic properties of materials is also complete, electromagnetic induction also half completed. Okay, be updated with all the concepts. If any doubts you can ask me. Okay, keep studying. Okay, thank you. Meet you in the next class.